Okay, I'm going to officially start my today's session, and today I'm going to discuss on a topic which is called hypothesis testing. But before I start discussing about the topic, I must say one thing to you. I'll be doing some sort of board work today. No more presentation of Excel sheet is there today. In my today's class, I shall be actually discussing the technicalities about how to do the hypothesis testing, and we shall start dealing with problems in the beginning. So my approach in this class will be to select a problem, and with respect to the given problem, I will try to help you out to find out the pros and cons about how to deal with the hypothesis testing. Okay, and during the process we'll keep on learning about the technicalities, about various other issues which should be taken care of in this particular regard. But before I start the discussion on hypothesis testing, I must say that whenever I'll be doing the board work, my video will remain off because my network connection here in Assam is very poor today, and I couldn't finish my earlier session with CSC section A. Okay, so we had some trouble over there. So therefore I have to keep my, and that's why I have been keeping my video switched off. If I want to discuss something with you face to face, then only I'm going to open my I am going to switch on my video. Otherwise, during the board work, my video will remain switched off. Okay. So with this, I'm going to share a white screen with you where I'm going to discuss a problem. I'm going to start directly from the problem, and gradually we'll get into the details of the theory. Okay. Hypothesis testing is a very large area, and it is also very true that to deal with hypothesis testing, we have to start from scratch. Okay, one has to start from scratch. We have to know some baseline works, and then we have to move, we can move further forward. But since we do not have much time uh, in our semester, the time frame which is there in our session, so therefore it is better if I start dealing with the problem itself, and then gradually we will understand what is happening over there. Okay, so let's begin our discussion on hypothesis testing. I'm switching off my video. My first problem of today's class is as follows. This is my problem number 1. A die is die or dice, whatever, is thrown 9,000 times and a throw of 3 or 4 is observed 3 to 40 times. Can we consider such a dice to be an unbiased one? This is the first question. So let us put 1 over here in the question, and part 2 of the problem is like this. Find the limits between which the probability of a throw of 3 or 4 lies. What I'm going to do is that I'm going to analyze the given situation and under the umbrella which is called hypothesis testing. And I'm going to dissect the problem part by part, and I'm going to make you understand what is happening over here. Okay. Before I start solving this particular problem, you see that the problem which is there in front of you is is a hypothetical problem, because actually with the help of some software, or hypothetically you are assuming the situation that if I have a die and if I have the chance of throwing that die 9,000 times, and if I observe the situation that in this 9,000 throws, I'm getting the phase 3 or phase 4 after throwing of the die, and it is appearing 3,240 times out of 9,000 times. Can we consider my dice to be a unbiased one, or should we consider the dice to be a biased die? None of us is actually very much interested about actually throwing the die 9,000 times. So what actually people do is that they actually use some kind of statistical software to analyze the given situation. But if you try to look at the problem carefully, and the things which are not directly written on in the statement, rather it is hidden behind the lines, I can talk about such situation. First of all, that if you want to find out where lies the, because hypothesis testing is all about giving some sort of conclusion about the population on the basis of sample measurements. So the question is, what is the population over here, and what is the sample? And if there is the sample, what is the size of the sample? That is pretty obvious, because actually hypothetically or with the help of some software, you are throwing your dice and 9,000 times. So that is your sample size. That is clear to all of us. But if this is the sample size, where is the population? That is a big question over here. So first of all, to start the problem, we have to set our goal. By setting the goal, I actually mean that you have to have some kind of hypothesis about the population on the basis of which this kind of testing will be done. Okay, so first of all, in this particular case, we have to identify the population over here. And if I look at the problem very carefully, we'll find that the population here is talking about the throwing of the die as many times as you can, as many times as it is humanly possible, or as many times as it is possible hypothetically. If someone says that if hypothetically we assume this particular die is being thrown infinitely many times, what do they actually mean by that? Some ideal die is there, generation after generation this die is being thrown by the statisticians, and the same results are being obtained. So that is a very hypothetical situation, a very ideal situation. So if this kind of scenario can also be assumed, because you can assume anything. So the main part is that if such kind of a die is existing, and if I keep on throwing that, I don't know how many times am I going to throw that die, but if I keep on going to throw that die, will it behave like the way it is behaving with respect to my sample? That is the question in this particular case. So my population here is the infinite throw of the die, or you can say finitely many times the die is thrown, but the number is actually not known. Because you can, at the same time, you can, on one side, you can think about your population as finite population of having some size. In another way, you can think of that population as being infinite. Okay, so we are going to study over that. The question is, if this is the scenario, what would be my hypothesis and how to study it? Okay, so I'm going to start my analysis of the given problem. Step number one is that we set our hypothesis. Okay. And in this particular case, we have to know one technicality about hypothesis testing. It is saying that there are two different types of hypothesis. One hypothesis is called null hypothesis, which is called hypothesis of no difference, and another is called alternative hypothesis, which is complementary to the null hypothesis. Try to understand this particular problem. If you find any sort of difficulties, you can ask me by raising your hand. And if you do not try to understand the given problem, you will face problem in every other subsequent problems of hypothesis testing. This is my base problem. So I want all of you to pay attention and try to understand what is happening, follow the steps that I am doing. What is step number one? In step number one, we want to set our hypothesis about the population. About the population. And specifically speaking, not actually about the population, about the population parameter, I want to place the hypothesis. I want to make my hypothesis. What is parameter? Parameter, you can say that any sort of population measurement is actually called parameter over here. So if you are talking about population mean, it is a parameter. If you are talking about population median, it is a parameter, and so on. Or you can look at it from a different perspective. A particular population is following some sort of probability distribution. Now the probability distribution that it is following, that probability distribution will be defined by its respective parameters, and that parameter can be the sample size, it can be the population proportion, it can be population standard deviation, it can not sample size, number of observations as many times as you can. I shouldn't use the word sample size with respect to population. Population proportion, population mean, population standard deviation, population variance, anything which is related to population. And these things will be in general called parameters. So when we are setting our null hypothesis, that null hypothesis will be set with respect to the population parameter. So I'm going to tell you how to set this null hypothesis. First of all, you have to know about the notations, some sort of notations which will be used over here. Okay. So the first notation that I'm going to use is for null hypothesis, and this notation is H0. Okay. And here capital H is standing for the word hypothesis, and 0, actually this is a kind of binary system where the answer is either yes or no. Okay, why is it so? Either your hypothesis is going to be true or your hypothesis is going to be false. So there are two possibilities. So therefore I'm saying that it is a binary system. Okay, so it is either true or it is either false. So we have used two binary digits, 0 and 1. So I am, for null hypothesis or hypothesis of no difference, I am setting the notation as H0, and its complementary hypothesis will be denoted by H1. Okay, that is the logic for which I'm actually selecting this. Now, if someone says that, can I take H1 to be null hypothesis and H0? The answer is right at this moment, you cannot do so, because it is universally accepted notation, and all over the world, H0 is universally considered to be the null hypothesis. Okay, so we have step number one, that we have to set our null hypothesis. And remember that this null hypothesis is actually a statement. This null hypothesis is not any a formula or any mathematical expression. It is a statement about the population parameter. Okay, so what sort of population parameter that we are going to consider over here? Now look at the problem carefully. In the problem is saying that you are throwing the die 9,000 times and the throw of 3 or 4 is observed 3240 times. Now, actually, in this particular problem, it is talking about sample proportion, because you know that the observation of 3 or 4 times of getting the observation of getting 3 or 4 these two phases 3240 times with respect to the number of times the operation is getting repeated. Actually, we are interested about the proportion, the sample proportion. We are interested about the ratio, that is 3240 out of 9,000. Okay, so but this ratio that we are talking about, but we can see from the line of the problem, it is actually the ratio related to sample, or you can call it a sample proportion. So if the sample proportion is my measurement, so obviously the corresponding population parameter will be the population proportion. Okay, so, and also another thing you observe that in the problem we have been asked whether this die is unbiased or not. Okay, now since null hypothesis is the hypothesis of no difference, what does this mean? This means that whatever manner or however you and wherever you actually throw the die, the results do not vary. What does this mean? This means that the probability of getting 3 or 4 remains constant throughout all the throws that you are making hypothetically. That means you are considering your dice to be an unbiased die. That will be a hypothesis of no difference. Since H0 is a statement, so here I am going to write that, yeah, I'm making this judgment that the given dice is unbiased. The given dice is unbiased. And if it is so, then the population proportion with respect to the given die, if it is denoted by capital P, that will be equals to 1/3. Why it is 1/3? Because see, probability of getting 3 or 4, that means it is actually equal to probability of getting 3 plus probability of getting 4. Because if we throw a die, these two events cannot happen simultaneously, and these two events are actually mutually exclusive. Now, if you consider your die to be unbiased, that means probability of for a single throw, probability of getting 3 is 1/6, and probability of getting 4 is 1/6. And you get by the axiom 3 of the probability theory, we get it as probability of A union B equals to probability of A plus probability of B, which is 2/6, and therefore it is 1/3. So when we consider the dice to be unbiased, the population probability or population proportion is equal to 1/3. That you are assuming. This is your assumption. Remember, hypothesis literally is also known as assumption. Okay. Statistically, we call it as hypothesis. Now, since alternative hypothesis is the complementary to the null hypothesis, so obviously the complementary event in this case will be die is biased. So if in null hypothesis you are taking the population proportion to be 1/3, in alternative hypothesis it will not be equal to 1/3. So we are going to write P not equals to 1/3. Okay. Now, if P is not equals to 1/3, then we suppose we are going to solve the problem, and after solving the problem, somehow we are getting that the alternative hypothesis is coming out to be true. Carefully observe that when we say that P not equals to 1/3, what does it actually mean? It means there are two possibilities. One possibility is that P is either less than 1/3 or P is greater than 1/3. Two possibilities are there. Okay. And therefore, if a null hypothesis is wrong and alternative hypothesis is right, then we actually do not know which of these two will hold good. So therefore, such type of testing, such type of hypothesis testing, where we consider in the null hypothesis, we consider the equality sign, and in alternative hypothesis, we consider the not equal to sign. Such a hypothesis actually called two-tailed test. Why? Because there are two tails. Either it can move. So if this is your normal curve, and this is your hypothesis of no difference, then if this is not true, this point is not invalid, then either you can move on the left direction or you can move on the right direction. We do not know which direction it's talking about. Say, for example, I'm just citing one example. So therefore, two tails are open, and therefore it is called two-tailed test. In some cases, it may so happen. So this is case one. Okay. In some other cases, there can be the possibility that by looking at the problem, you find that in null hypothesis, you are considering the equality sign, and in alternative hypothesis, you are considering less than sign. Or it may so happen that in null hypothesis, you are considering equal to sign, and in alternative hypothesis, you are considering greater than sign. So in these cases, you are actually sure about your normal curve. If I'm talking about the normal population, that if this point, I'm not sure about this point, then for the case sub case one, I have this left tail open, and for this sub case two, I have this right tail open. Okay, so such a either of this will happen, I'm sure about that from by the given condition of the problem. So in such a case, these tests will be called one-tail test. One-tail test. Okay, so in both the cases, one tail is open. So if I try to look at our problem, given problem where we set our null hypothesis, we have found that in the dice problem, we are actually dealing with a two-tail test, because in null hypothesis, equality sign is there. In alternative hypothesis, not equal to sign is there. So that is another thing that you have to test properly, that whether you are dealing with a one-tailed system or you are dealing with a two-tailed system. Once you make this judgment, and I'm actually going to tell you about why we always consider the inequality sign in the null hypothesis. You can ask me this question, that can I reverse the scenario? Can I consider the not inequality symbols in the null hypothesis and equality symbol in the alternative hypothesis? Or here, can we interchange the position of these two symbols? The answer is no, you cannot do so. The reason for doing this is, since you have considered the null hypothesis as the hypothesis of no difference, and this is the definition of null hypothesis, so we want to test the population with some statistical tool under the assumption that H0 is true. So in H0, what have you considered? In H0, you have considered capital P is equal to 1/3. So in the statistical tool that you are going to consider in this particular case, there will be some sort of reflection about capital P. Now, if since you have assumed that capital P equals to 1/3, you will be able to put capital P in the formula. But if you interchange the symbols not equal to symbol and equal to symbol in between them, then that, since you are testing under the assumption of null hypothesis, you will not be able to put the value of capital P into the respective formula. And that's why equality signs are always present in the null hypothesis and not in the alternative hypothesis. Okay, so remember this particular point. So once we set up the null hypothesis and the alternative hypothesis, then we have to choose our statistical tool. So step number 2 is that choose an appropriate statistical tool. Depending upon the system, there are several statistical tools available. You have to choose an appropriate one, and that will be decided by you on the basis of the system you are working on. And with the practice, you can identify pretty well what sort of statistical tool will be appropriate to your given system. Since you know very little about hypothesis testing, and since this is the first problem that you are doing over here, in this particular case, I'm actually going to help you to find out an appropriate statistical tool. The system which I am actually dealing with right now, it is a special type of hypothesis testing, which is called test of single proportion. So I'm writing the name over here. The test which I have selected to discuss the hypothesis testing, it is called test of single proportion. Single proportion of what? Single proportion of population. Someone wants to say something, I think, Shuman. So you want to say something, you can ask me. You raised your hand. You can unmute yourself and you can ask me the question. So test of single proportion of a test of single proportion is the test that I'm actually going to show you over here. And single proportion, the word single proportion actually means I'm talking about capital P, which is the population proportion, and only single parameter is being chosen. In such a case, if this is the case I'm dealing with, in this case, under the null hypothesis, so this word is very important. In hypothesis testing, you will often find this sort of word. Under the null hypothesis, the statistical tool that I'm going to apply is capital Z, which is defined as x minus ex by root over vx. A standardized variable will be selected over here. And in the current scenario, this ex will be n into capital P, and this vx will be n into capital P into capital Q, just like the binomial system we studied in our earlier course classes. Okay, so it is behaving like the binomial system. This test that I'm actually following over here is actually known as Z test. This test I'm following is called Z test, or in some books it is called normal test. Because you know that normal distribution is a special case of binomial distribution under the assumption that n is pretty large and the probability of success is pretty small. Now carefully observe in the formula, this item capital P is present. Okay, and we are going to test the hypothesis under the assumption of H0. Now, if I do not write P equals to 1/3 in H0, we will not be able to put it over here. Since we have written P equal to 1/3, we are allowed to put P, the value of P in the respective formula. So that's why equality sign should be present in null hypothesis. Now we have to find out the value of capital P. and value of capital Q. But what is capital P? Capital P is actually the population proportion. Capital P is called the population proportion, and capital Q is counter to capital P, which is 1 minus capital P, complementary probability. You know it from binomial distribution. Here at this stage, you have to know one fact, and this fact is, in your syllabus, there is a gap. No discussion about estimation theory is present in your syllabus. That's why I have not discussed estimation theory with you. I have directly come to the point of hypothesis testing. But if you take any statistics book and the book which I've shared with you, there you'll find that before they get into hypothesis testing's discussion, estimation theory was discussed. Estimation theory, in brief, talks about what sort of statistic best estimates the parameter. This is the main fundamental knowledge that we gather from the estimation theory. What is statistic? Any sample measurement is called statistic. And any population measurement is called parameter. Okay, and it has been observed, various cases were studied over there, and in one such case it has been observed that sample proportion best estimates population proportion. It is a result from the estimation theory that I'm not going to deduce in your class, and I'm not going to discuss in details mathematically, because this idea of estimation theory is not there in your syllabus. I'm going to use this fundamental criteria into our problem. Why should I be bothered about this fundamental criteria? Just look at the formula. You are dealing with, in the formula, you are dealing with capital P and capital Q. These are all about population proportion. But any sane person can say that population proportion or population measurements cannot be made. If we can make population measurements, then there is no point in studying sampling theory. Since population measurements cannot be done, that's why we study this. We study the samples, isn't it? So capital P is the population. Capital P is the population proportion, and capital Q is this population proportion, complementary population proportion. I will try to find out whether I can say anything about capital P or not. If I can see something about capital P from the given problem, then it is okay, no problem with that. I can substitute the value. But if I cannot say anything about population proportion directly from the given problem, then I have to guess it by sample proportion. I told you that there is some kind of problem over here today. So see, I just lost all my board works over there. No problem with that. I can recall where they are in the problem. So I hope that you have taken the screenshot of the given of that page. So I'm just starting from what I was talking about. I was talking about the formula. That is the formula I was talking about, x minus npq square root. Now I was talking that in the problem, I will try to look for whether I can guess about capital P. Suppose we cannot guess about capital P, then what we will do? Some values are calculated from all these. We can find value of Z over here. This is the calculation step that I'm talking about. Now I am asking all the students to please quickly try to calculate the value of Z and write in the chat box. I do not have with me any calculator right now, so your calculation will help me in this regard. So please do the calculation and tell me what values you are getting. I'm waiting for your reply. $5.36. So approximately 5.36 is the answer. Okay. Now the calculation part is all right. Now after the calculation, if we were